So, my dear students, in the previous class, we have discussed output equation and some basics of electromagnetism, and also factors affecting average flux density and ampere conductor per meter. With that, how to separate D and L also discussed. Today, I am going to. So now these are the pictures of the stator core. Stator, it is made up of thin laminated stampings. So thickness is around 0.3 to 0.5 mm. So these stampings are very thin and varnish coated, and these are stacked throughout the length of the this is the length. Okay, they are stacked together. So to reduce hysteresis losses, they are made up of thin and laminated one. So you can see here in this stamping there are number of stator slots. Along with that, tooths are tooth is there. Okay. So there are a number of stator slots embedded over the periphery of the stampings. So there are, you can see here, these are the slots, okay, where the winding is embedded, and along with that, stator tooth will come. Okay. So now you can see in this picture, the winding is embedded in the slot. So when you give the three-phase supply in to this winding, in the air gap, rotating magnetic field is produced here. Okay. So actually here in the stator, there will not be any physical poles are existing. The type of winding, it creates a rotating magnetic field when supply is given. So now you can see here this stator core is inserted in the frame. This is the core, and windings are terminated at the terminal box, where you can give input supply to winding. Okay, this is the rotor and this is the stator. Okay, in the stator design, we are about to discuss what are the number of turns per phase, what is the cross-sectional area of the conductor, then how many number of slots should be there, and what are the dimensions of the slot, what are the dimensions of the tooth, all those things we are going to discuss. Now coming to turns per phase, so we have this basic equation. EPH is equal to 4.44 pi m TPH kWs. So now this is, we know the EPH, applied voltage across winding. Okay. So now TPH I want to calculate. Here TPH is unknown. Okay. KWs is winding factor. It is around 0.955. And phi m is also unknown. So we have to find out phi m. We have B average is equal to pi m by A. So pi m is equal to, you take this B average into A. B average into area of the pole. So area of the pole is given by pi d L divided by P. So you can see here, this is pi d by P. Okay, this is L. This is L. Now this is the flux. Okay, flux is generated in this pole area, under this pole area. Okay, so this is pi d, this is L. So pi d L by P. Pi d L by P, it will give pole area for one pole. So now this is equal to B average. Tau is the pole pitch, pi d by P into L. So now once you find out pi m, so we can substitute here this pi m. Okay, so that we can find out TPH. Rest of the values are known. EPH, frequency we know, KWs we know. We can find out TPH. So sometimes TS is also used. ES is also used instead of EPH and TS. So now conductors per phase is equal to 2 pH. Conductors per phase is equal to 2 pH. So now you can see here in this diagram, this is the conductors. These are the conductors. Okay. So this is one conductor, this is one conductor. Two conductors constitutes one turn. This is one turn, like this. Okay. So for one turn, two conductors are required. So TPH for one turn, if you substitute 1 here, 2 into 1, conductors per phase is equal to 2. The total number of conductors for 3-phase, this is for 1 phase. We have to multiply 3 for 3-phase, 3 into 2 into 6, 3 into 2 into TPH. This is equal to 6 TPH. So coming to cross-sectional area of the stator conductor. To find out cross-sectional area of the stator conductor, consider this equation. Q in kVA is equal to 3 EPH IPH into 10 raised to minus 3. So because this is in kVA, this is in volt ampere. So to convert volt ampere into kVA, we have to multiply with 10 raised to minus 3, or that is nothing but dividing this by 1000. So from this equation, IPH is equal to Q into 1000 divided by EPH. Now phase current we can find out using this equation. Let IZ be the current through the conductor. See here, this is current through the conductor. So this is the case where two parallel paths are there. This is the IPH. Now IPH is dividing into two paths, here and here. Okay, this is the IZ. This is the IZ. Okay, this is also IZ. Now depending upon the current through the conductor, we have to find out, we have to calculate cross-sectional area of the conductor. So now AS cross-sectional area of the conductor is equal to IZ by delta S. Delta S is the current density. So IZ is equal to IPH divided by AA is the number of parallel paths. So now delta S we can assume 3 to 5 ampere per mm square. Once you find out delta S cross-sectional area, you can find out per phase stator resistance RS. Stator resistance per phase. This is equal to rho LMTS TS by AS. This rho is the resistivity. LMTS is the length of mean turn of stator winding. Length of mean turn of stator winding. TS is the turns per phase. And AS is the cross-sectional area. Once we find out RS, we can find out the copper loss of the stator also. So I square RS, 3 into I square RS. Okay. You will understand how to calculate all those dimensions by analyzing the equation. Okay. Now the next, once after finding out the stator details, now moving on to the air gap length. Okay. So now you can see that there is an air gap between stator and rotor. Stator and rotor. The air gap you may design with minimum length. Also, it may be possible. Possible to have larger air gap length. So, if you have precise manufacturing technique, the air gap length can be minimized. Minimum air gap length can be kept. If there is no facility, if there is no precise manufacturing lengths are there, if there is no advanced techniques are there, the length of the air gap becomes large, because rotor has to rotate in the air gap. Okay, what happens if proper air gap is not given? Rotor may touch the stator. If proper alignment is not there of shaft, then rotor may touch the stator. So that is the reason a proper air gap length has to be given. So now this air gap length, it is going to affect the power factor of the machine. Power factor of the machine. We know that the MMF required to send the flux through the air gap is proportional to the product of flux density and length of air gap. This MMF is equal to flux multiplied by reluctance. That is nothing but flux is nothing but flux density proportional to reluctance. That is, reluctance is proportional to Lg. Now we can tell that the MMF required is directly proportional to Lg, length of air gap. The MMF required to force the flux through the air gap, it is proportional to the length of air gap. If air gap length is large, more MMF is required, more magnetomotive force is required. So if air gap length is large, larger MMF is required, hence larger magnetizing current is drawn. Larger magnetizing current is drawn. If magnetizing current drawn is large, okay, the power factor becomes low. If the air gap length is small, the small MMF is required, hence small magnetizing current is drawn. If magnetizing current drawn is small, the power factor will become high. Power factor will become high. So now what we conclude that with vector diagram also we'll see. See, this is the vector diagram. Okay, this is for smaller air gap length. So for smaller air gap length, smaller magnetizing current is drawn. Small value of magnetizing current is drawn. So this we can see in the vector diagram, angle between Vs and Is1 is pi 1. So this, and similarly if we see for large air gap length, the magnetomotive force mmf required will be large. Then for higher value of mmf, the magnetizing current drawn will be more. Because of that, the angle pi 2 between Vs and Is2, that is large. So that is large means cos pi 2 becomes less. Power factor will be low. Power factor will be low. So now what it indicates that for smaller air gap length, the power factor will be high. The operating power factor will be high. For larger air gap length, operating power factor will be low. So when customer asks to design machine with high power factor, we should minimize the air gap length. Air gap length should be minimum. Okay. So for that, we should see what kind of manufacturing techniques we have. According to that, we have to manufacture the machine so that we can have a minimum air gap length and higher power factor. Now coming to overload capacity, as the air gap increases, that as the length of air gap increases, the zigzag leakage reactance decreases, which is a major part of the leakage reactance excess, and hence leakage reactance decreases. Understood? As the length of air gap increases, the zigzag leakage reactance decreases. This zigzag leakage reactance is major part of the leakage reactance excess, and hence leakage reactance decreases. Leakage reactance decreases. So now these are the two circle diagrams. Okay, with higher value of leakage reactance, with lower value of leakage reactance. So now when leakage reactance decreases, this decreases, this is decreases, then diameter of the circle diagram is large, and this will give large value of overload capacity. Overload capacity is a ratio of Mn by, this is Mn by Al. Mn by Al, you can see here Mn is this much large, Al is this. So when air gap length increases, the ratio Mn by Al will be large, overload capacity will be large. So when air gap length is small, the zigzag leakage reactance increases, and excess will increase. This leakage reactance will increase. Because of that, the diameter of the circle diagram will be less. Because of that, overload capacity decreases. You will get lower value of overload capacity. Okay. So overload capacity from the circle diagram, you can find out the ratio of Mn by Al. Mn by Al. Okay. So it is found that for larger air gap length results in lower value of excess, due to which diameter of the circle diagram is large and hence overload capacity is large. Now coming to pulsation losses, with large length of air gap, the variation of reluctance due to slotting is small. If air gap length is large, the variation of reluctance due to slotting is small. Therefore, pulsation loss is less with large air gap. Pulsation loss is less with large air gap. If air gap is large, okay, then what happens? Reluctance variation in the air gap is due to slotting is small. So if that variation is small, and there will be a flux pulsation variation also minimum. Because of that, flux pulsation losses will reduce. Now coming to noise, If the air gap length is large, the variation of zigzag reactance is less, producing less noise. You might hear some humming sound. On motor runs, you may find some sound. Okay, so that is because of this. Because of this, the variation, because of the variation of zigzag leakage reactance, you will find the sound. If air gap length is large, the variation of zigzag leakage reactance is less. You will get less sound. Otherwise, if small air gap length is small, the variation of zigzag leakage reactance is more. You may find higher noise. Now coming to cooling, if the air gap length is large, cooling at the gap surfaces, especially when the fan is fitted for the circulation of air, is better. Cooling air passes through that air gap, and through which the heat will be extracted. Cooling effect will be. Now coming to unbalanced magnetic pull. So if the air gap is small, if length of air gap is small, even a small deflection or eccentricity of the shaft would produce larger irregularity in the length of air gap and is responsible for the production of large unbalanced magnetic pull, which has tendency to bend the shaft, resulting in fouling of the rotor with stator. If the length of the air gap of a machine is large, a small eccentricity would not be able to produce noticeable unbalanced magnetic pull. So we know that there is a air gap length between stator and rotor. So that air gap length must be uniform. Okay, but due to manufacturing defects, if some of the portion, if that air gap length becomes less compared to other area, now what happens when it starts rotating, in the area of air gap length where the minimum length is there, okay, because of that error in the because of manufacturing defects, now what happens when it rotates, there will be a large magnetic pull is occurring. Okay, unbalanced, what you call unbalanced magnetic pull is occurring in that area where the air gap length is minimum. So it will give jerk. So because of that, the shaft starts bending, and shaft may bend. When shafts bend, it may lead to what rotor may go and touch the stator. That is called fouling of the rotor with stator. So once it touches, rotor becomes jam, winding may burn. So if air gap length is large, such what unmagnetic pulls are unnoticeable. Even though for small eccentricity, these unbalanced magnetic pulls are unnoticeable. It will not have effect on that one. That is the added advantage. So finally, there is a empirical formula to calculate length of air gap. Lg is equal to 0.2 plus 2 into root of d into L mm. This is Lg in terms of